Hello everyone, my name is Darian Castle, and today I'm going to be talking to you about OmniCrawl, comprehensive measurement of web tracking with real desktop and mobile browsers. This is joint work between myself and my colleagues at several institutions. To begin, I'm going to talk about the concept of browser fingerprinting, in particular as it applies to mobile browsers. So modern mobile phones and desktop computers have a complex configuration of both hardware and software. If you think about a phone that you may have a camera, a microphone, a gyroscope, an accelerometer, a GPS module. These particular hardware components make up the hardware characteristics of the device. Likewise, devices also have a suite of software characteristics, such as the operating system that the device is running, the browser that a user is using, as well as its configuration and particular version, as well as things that people don't think about as often, such as which fonts are installed on the device. Browser fingerprinting is what occurs when a tracker is able to gather enough of these hardware and software characteristics to be able to uniquely identify a user's browser across website visits. With that in mind, we'll now look at the rise of mobile browsing, which is the second piece of motivation for our work. What we saw over the past decade is a steady increase in the market share of mobile browsing relative to desktop browsing, culminating in 2016, where we see that mobile browsing actually overtook desktop browsing as the most popular way that people are accessing the web. This is important and a challenge for web privacy measurement researchers because mobile browsers run on mobile devices that have additional sensors as compared to desktop devices. And mobile browsers expose access to these sensors via sensor APIs that can be used for tracking. However, what we found, at least at the time of this paper, is that there were few studies that were taking the vantage point of mobile browsing, most of them being focused on desktop browsing. We also found some cases of prior work using emulated mobile browsers, which are desktop browsers running on desktop devices that have been configured to appear to websites as mobile browsers. These two observations led us to two research questions. First, how do mainstream mobile and desktop browsers actually compare in terms of tracking and advertising? And second, is it ecologically valid to use emulated browsers in a web measurement study? Our final piece of motivation for this work was the rise of privacy-focused browsers. What we found on the Android marketplace is that there were many mobile browsers that were claiming to be able to enhance users' privacy in one way or another. For example, Firefox Focus claims to build a block known ad analytics and social trackers. DuckDuckGo claims to be able to stop advertisers from tracking you on the sites you visit. Ghostery claims to be able to block trackers and anonymize your data to further protect your privacy. In total, we gathered 5 browsers making these such claims that had more than 1 million downloads each. That's Brave, Firefox Focus, the Tor browser, DuckDuckGo, and Ghostery. Of these browsers, we sought to ask 2 research questions. First, how effective are these privacy-focused browsers at blocking tracking and advertising? And second, what are the strengths and weaknesses of individual privacy-focused browsers? Are some more effective than others? In order to answer these research questions, we needed to develop an infrastructure that was capable of doing synchronized comparison of a single website across multiple different desktop and mobile browsers. We developed OmniCrawl, and it works like this. First, we have a main crawler that dispatches URLs to be visited to a suite of desktop browsers and mobile browsers running on real devices. These browsers will dispatch a request for that URL to our proxy, which will forward the request to a web server, and we'll get back a response, which will allow us to determine what first and third parties were loaded. Then, if the response has JavaScript, that JavaScript will be instrumented before it is loaded by the browsers. This instrumentation will allow us to log access to browser APIs. These access logs will later then be used to determine what APIs were accessed, as well as whether potential fingerprinting was occurring on the page. Finally, the proxy will send back a signal to indicate that that URL was visited so that we can synchronize between all of our browsers. We set up this infrastructure in North America across 2 desktop browsers of devices, as well as 9 Android 8.1 mobile phones, each running 1 browser. We also replicated the setup in Asia for a total of 42 browsers running across 22 physical devices. However, for the purpose of this talk, we'll be focusing on the results from the North American dataset. Having developed this infrastructure, our goal in crawling was to crawl both popular, high-ranked websites as well as lower-ranked websites that are less popular in order to gain a balanced picture of the current state of web tracking. To do this, we selected websites from the Trenco ranking, which we used over the more well-known Alexa ranking for its increased stability and manipulation resistance. From the Trenco ranking, we selected 20,000 websites, all of the top 10,000 websites, as well as an additional 10,000 websites selected uniformly, 1 out of every 10, from rank 10,000 to rank 110,000, in order to ensure that our dataset also contained lesser-known sites. Having gathered this dataset, our goal in our analysis was to be able to measure third-party tracking and advertising, as well as potential fingerprinting behaviors of websites. To do this, we took the HTTP request data from the proxy and first categorized requests as either being first or third party, and the second classified request as being potentially tracking and advertising by checking to see if the request was matched by one of many block lists we included in our crawl, and then associating a third-party tracking and advertising entity with a request using a tool called Web X-ray, which, for example, would allow you to take a request to Google Analytics and associate it with the entity Google. Next, on the API access side, we first categorized APIs into a set of sensitive API categories by function, such as audio, automation, canvas, and so on. And then we used a set of fingerprinting heuristics that were sourced from prior work to determine whether potential kinds of fingerprinting were occurring on the page, such as WebRTC fingerprinting, audio, font, canvas, or WebGL. Having gathered this data set, I want to mention one thing, which is that we used a statistical testing methodology to establish the significance of our results. If over the next few slides I mention a significant difference, I specifically mean a statistically significant difference. Okay, I won't have time to go over all of our results in detail, so instead I'm going to be presenting a summary of some of our key results. First, for our first research question, which asks, how do mainstream mobile and desktop browsers compare in terms of tracking and advertising? What we found surprisingly is that the mobile-specific or mobile-only and desktop-specific third-party tracking and advertising entities only accounted for 0.45% of the requests in our crawl, indicating a surprisingly low impact. This, as well as other data, led us to conclude that the ecosystems of third-party tracking and advertising entities are actually more homogeneous across mobile and desktop than was previously thought. However, what we found is that while the third-party tracking and advertising entities are essentially the same between mobile and desktop, they actually behave differently on mobile. On mobile, we saw more accesses to APIs that were indicative of fingerprinting, such as a 54% increase in the screen API accesses, as well as a 21% increase in fingerprinting heuristics that pointed to potential WebRTC fingerprinting occurring on the page. Next, looking at our second research question, which asks whether it is ecologically valid to use emulated browsers in a web measurement study. What we found is that OpenWPM Mobile, which takes desktop Firefox running on a desktop device and configures it to look like mobile Firefox running on a mobile device, actually experienced significantly more requests and API accesses than the real mobile Firefox running on a mobile device. In particular, we saw 6% more third-party tracking and advertising requests, as well as 50% more accesses to the plugin API, which is actually desktop specific. This, as well as additional data, allowed us to conclude that emulated browsers may not actually be suitable for web measurement studies that are attempting to measure third-party request or browser API accesses. Now, shifting gears to look at our privacy-focused browsers, we first ask, how effective are privacy-focused browsers at blocking tracking and advertising? And what we find is that while privacy-focused browsers as a group do actually reduce third-party tracking and advertising on average, they do not uniformly reduce third-party tracking and advertising requests. In particular, we found that they are only most effective for the most highly prevalent entities, such as the top three, Google, Facebook, and Adobe systems, where, for example, we see a 60% reduction in third-party tracking and advertising requests attributable to Google. Next, looking at our last question, which asks, what are the strengths and weaknesses of the individual privacy-focused browsers? What we find is that while they are generally effective at reducing third-party tracking and advertising, they actually can vary widely in their effectiveness. For example, looking at third-party tracking and advertising requests, we see that the Tor browser, for example, has 13 times as many of these requests as Firefox Focus. Considering API accesses, we see that the Brave browser actually has 25% less than the privacy-focused browsers as a group. What we also found concerningly is that there were several privacy-focused browsers that deviated from what they said in their marketing claims. For example, the Tor browser in its marketing claims claimed to be able to do tracker blocking. However, we found that this claim was unsupported because at the time of our study, the Tor browser did not actually include any ad or tracker blocking plugins. Okay, with these answers to the research questions in mind, we developed a set of recommendations both for future web measurement studies and for privacy-focused browser vendors. First, looking at our recommendations for future web measurement study design. First, we recommend that future web measurement studies avoid the use of emulated mobile browsers when mobile-specific measurements are required. Emulated mobile browsers must emulate all of the hardware-level characteristics of real mobile devices, which is extremely difficult to do due to hardware-level variations and specific components that these browsers use. As a result, it's quite difficult to get the emulation correct, and there is a high likelihood that there will be differences in the API access results that will lead websites to be able to detect that the emulated mobile browser is actually a desktop browser running on a desktop device. Second, we recommend that future web measurement studies modify off-the-shelf browser drivers such as Selenium before using them. We found, for example, that Selenium will inject properties into the web page, into the DOM specifically, that websites can and do detect. This can lead to the website modifying its behavior in a way that affects the ecological validity of the study. Next, looking at our recommendations for privacy-focused browser vendors. First, we recommend that they clarify the concrete implications of all their marketing claims and not use unsubstantiated terminology such as tracker blocking without really explaining what the implications are. This will allow users to better pick the browser that meets their specific privacy needs. Second, we recommend that privacy-focused browser vendors offer users much more fine-grained control over blocking comprehensiveness. We've found several cases where browsers will select between the trade-off between performance and blocking comprehensiveness for users without really offering users a choice in how that's configured. However, we suggest that users be given more control so they can pick the right balance between those two for their privacy needs. Finally, what I want to say is that we have many more details available in the paper, so please check that out. And we also have an artifact available at this URL. Using this artifact will allow you to run OmniCrawl with a selection of browsers and replicate the results of our measurement study. Thank you so much for your time and attention.